today's topic is heat capacities. Like, so heat capacity, we have to discuss about the two types of heat. First is specific heat capacity of gases. We have specific heat capacities of gases. Now, in specific heat capacities of gases, what happens? I've told you the formula. The formula is Q upon M delta T. Now, what happens in this? So, specific heat capacity is actually the amount of heat required amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. Amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. For example, the specific heat of water is 4.2 joule, yes, unit mass per gram per degree Celsius. So it's the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. Right? Here I have told you, like, we have two types of processes, that is iso. We have many types of processes, but the main which we have to study is isothermal. The first type of process is isothermal process, and the second is isothermal process, and the second type of process is adiabatic process. First type of process is isothermal and the second type is adiabatic. I have told you earlier also, iso means same, thermal means temperature, means in this process the temperature remains constant, therefore delta T is equals to 0. And what is the formula of heat capacity? Specific heat capacity is Q, heat upon M delta T. Since delta T is equals to 0, the specific heat is infinite. Yes, and in case of adiabatic process, the heat change is 0. Delta Q is equals to 0 means the heat exchange, yes, is 0. So what happens? The value of C is Q by M delta T. So this value becomes 0. So if I ask you the value of heat capacity, it ranges from 0 to infinite. Yes, heat capacity can have for any substance, it can have any value from 0 to infinite. Yes, now we'll calculate the specific heat capacity at constant volume. Specific heat capacity at constant volume, which is equals to C. C is equals to Q upon M delta T. So the amount of heat required at constant C, amount of heat required to raise the temperature of 1 gram of substance. Yes. Amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius, right? It's CV, so Q is equals to CV. Is specific heat capacity at constant volume, amount of heat required to raise the temperature of 1 degree Celsius, to raise the temperature of 1 gram of substance by 1 degree Celsius at constant volume is CV. Yes. Second part we have to study is specific heat capacity at constant pressure. It will be similar. Now what happens? specific heat capacity is at constant pressure. It is Cp is equals to Q by m delta T. Now what happens? We have for 1 gram of gas, amount of heat required to raise the temperature of 1 gram of gas by 1 degree Celsius at constant pressure is Cp. So we can say this Q will be equal to Cp. Next, molar heat capacity. Next topic is, so this is what we have to study actually, molar heat capacity. This is what we have to study. Molar heat capacity is because the amount of gas we take, generally we take the amount of gas in moles only. This is what we have to study. Amount of gas, amount of heat required to raise the amount of heat required to raise the temperature of to raise the temperature of 1 mole of substance. Amount of heat required to raise the temperature of 1 mole of substance by 1 degree Celsius. Now what happens here? The C is capital, and in case of specific heat capacities it's known by small c. So molar heat capacity at constant volume, it will be Cv is equals to Q upon m delta T. Yes, actually here instead of mass, because we are taking about number of moles, so I will take n. Yes, and where n is the number of moles of a substance, right? Cv is equals to Q upon n delta T. Next, if we talk about molar heat capacity at constant pressure, molar heat capacity at constant pressure, Cp is equals to Q by number of moles. Now specific heat capacity is for 1 gram of a substance and molar heat capacity is for 1 mole of a substance. So let us try to find out the relation between the two, how these two terms are related to each other with the help of a question or numerical, you can say. Like for example we have oxygen gas, and for oxygen gas the value of Cv, this is small cv, that is specific heat capacity, that is specific capacity is equals to X. Now for 1 gram of substance, we have for 1 gram of substance, right? The heat required to raise the temperature is Cv. Now what is you have to calculate the value of capital Cv. Now what is capital Cv? It is heat required to raise the temperature for 1 mole of substance. So you have to tell the relation between capital Cv and small cv. See, small cv is actually the heat required to raise the temperature for 1 gram of substance by 1 degree Celsius, but whereas capital Cv is for 1 mole. Therefore, we can write it as, we know that in 1 mole we have 32 grams of oxygen, right? In 1 gram, the value of Cv is X. So for Cv it will be 32X. As simple as this. So therefore we can write it as, in general, if we want to write, we can write it as Cv, capital Cv is equals to molar mass into small cv, and capital Cp, molar mass into small cv. I hope this much is clear to you. Next, next a very important equation that you have to remember is, this is capital C. Capital Cp minus Cv is equals to R. Yes, it's true for ideal gas, or you can write it as NR. For N is equals to R for 1 mole of gas, and for NR is for for ideal gas. If it's 1 mole, you write it as R. If it's n moles, you write it as, or you simply wait. You learn it at Cp minus Cv. And for 1 mole, the value will become Cp minus Cv is equal to R. I hope this much is clear to you. Now, but let's try one question on this concept. Question is, for nitrogen gas, the value of Cp minus Cv is equals to, and they had given you options also. First option is 14R, second option is R by 14, third is 28R, and fourth option is R by 28. So see, we know that for ideal gas the value Cp minus Cv is equals to R. It means they are asking the value of small Cp and small Cv. What is the small Cp? Is equals to molar or Cv. It will remain same, molar mass into small Cp. So can I simply write it? We know that for ideal gas, capital Cp minus capital Cv is equals to R. Yes, Cp minus Cv is equals to R. Now what happens? This Cp, I can write it as molar mass. That is, what is the molar mass of nitrogen? 14 2 is 9, 28 Cp minus 28 Cv is equals to R. So therefore, Cp minus Cv is equals to R by 28. So option D is the correct answer. Next. So let's summarize this video. Once again, what we have learned Cp is equals to heat at constant pressure upon N delta T, and Cv is equals to heat at constant volume by N delta T. And another way of writing these equations are, if you want to find out the value of heat at constant pressure, it is Cp Ncp delta T, and heat at constant volume is Ncv delta T. Next, I have to tell you the relation between these heat capacities and degree of freedom. See, degree of freedom you will study in detail in your physics thermodynamics, but I'll just give you an idea. Degree of freedom, yes, you can say degree of freedom or atomicity. It's one and the same thing of a gas. Degree of freedom or atomicity of a gas. The value of Cv, that is heat capacity at constant volume, is equals to F by 2R, right? Yes. So therefore Cv, what is Cp? Cp is equals to Cv plus R. So therefore Cp is equals to F upon 2R plus 1. Rather than learning this, you can simply learn Cv, the value of Cv you can learn, and Cp we can calculate by using Cp equals to Cv plus R. So for monoatomic gases, you just learn this small points. For monatomic gases, the value of F is 3. What is monatomic? Like helium, argon, neon. Yes, these are gases, like these are monatomic gases. Diatomic gas, the value of F is 5, that is O2, N2. And for polyatomic, H2, polyatomic, where the atoms are more than 2, it can be 3 or more. Polyatomic, the value of F, degree of freedom, is 6. These are all experimental data, okay, like ozone, O3. So next, Let's using this. Let's summarize this in using a tabular form. So just a minute. You Cp minus Cv is equals to R. This is one relation that you have to remember. Another relation that you have to remember is Cp minus Cv is equals to gamma. These two relations. Just a minute. Cp upon Cv is equals to gamma, right? Now what happens here? I'll write F that is, yes, F degree of freedom, value of Cv, Cp, gamma. Yes, gamma is equal to Cp by C. Degree of freedom. Degree of freedom for a monatomic gas. For a monoatomic gas, degree of freedom is 3. Therefore, Cp will be Cv is equal to 3 upon 2 R, and Cp will be Cv plus R, that is 5 by 2 R. So gamma will be, what is gamma? 5.3. Yes. So it will be 3 ones are 3, 1.66. The value of gamma. Next, we have to study these relations for all the three types of gas: mono, di, and poly. Diatomic gas. Now, in case of diatomic gas, the degree of freedom, it's, what is the degree of freedom? 5. So Cv will be 5.2 R, Cp will be 7 by 2 R. Yes, and Cp by Cv, that is gamma, is equals to Cp by Cv, that is 7 upon 5. Yes, Cp by Cv 7 by 5, which is 1.4. Next, for polyatomic. Because it's easier, right? If the data is given in tabular form, it's easier. You can do the comparison also, and you can easily learn. Polyatomic. In case of polyatomic gas, degree of freedom is 6. So Cv is equal to 6 by 3R. Cp will be 4R. So the value of gamma will be 4 upon 3, which is 1.33. So if we compare these values, we deduce that the gamma value of monoatomic gas, it's maximum for monatomic gas, then for diatomic, yes, and it's least for polyatomic gas. And this is a very useful relation, right? So I hope this much is clear to you.